Okay, so let's go ahead and get started with deep neural nets or deep neural networks, otherwise referred to as or abbreviated as NNs. Okay, so let's go ahead and get started. So what is a neural network? So neural networks are inspired or were inspired by biological neurons in the brain. So if we look at this picture here of a biological neuron, we see dendrites, a nucleus, and an axon, and then several other pieces here. Well, in this biological model, dendrites will feed through signals to the nucleus, and those signals will stimulate the nucleus and activate a signal that passes through the axon. So we have signals that go into the dendrites, go into the nucleus, and depending on the strength of those signals, the axon will fire. So imagine, for example, you're cooking in the kitchen and you accidentally grab a hot pan right as you're about to drop a potato or something, right? So in your right hand, you're grabbing the hot pan, and your left hand, you're dropping a potato. What should you do? So a combination of biological neurons will receive signals. Some signals will be that the potato is falling out of your hand. Other signals will tell you that the pan that you just grabbed is hot. And through some combinations of these, the signals that the neurons receive will fire and tell you whether or not to lift your hand off the pan or to grab the potato. So in this model, there's strength associated, or we assume in a kind of a vague way that the signals have certain strengths that are learned over time via some evolutionary process. So when we design a computational unit to model this, which we call an artificial neuron, we have input that goes in to the dendrites with weights that tell the nucleus how to fire, right? So if the weights are strong enough for a given pain, for example, burning your hand, then certain neurons in your brain will fire saying to lift your hand off that pan, as opposed to just letting the potato fall, which other neurons maybe wouldn't fire if this one was firing. So through combinations and linking together of artificial neurons, we hope to mimic the process of learning in the brain. So how does this work? Well, each input signal, or a feature measure in our case for supervised learning, is scaled by the first layer weights, which in turn affects the function computed at the unit. So if we go back here, we have this unit, this artificial neuron, which is just a computational unit. In other words, it is a function of the input weights, right? So the input signal. So the weights are going to scale the input signal, which affects the output of that neuron. So in all, once you have a bunch of neurons that are connected, the neural net then computes a function of the input signal by propagating the signal or the computed values from the input signal to the output neurons, and it uses the weights as intermediate parameters. So you'll have a sequence of neurons that are layered together, one layer after another, and there's weights between each of those layers, and the signal is weighted, squeezed, adjusted throughout the forward pass, which we'll learn what that is in a second, of this system, which in turn, it computes a function. It's going to tell the network whether or not something is occurring or not, or whether or not to take an action or not. So learning occurs by adjusting the weights in this network. So imagine there's weights connecting thousands of neurons together, and if you adjust those weights, the input signal will vary and the output will differ based off of the weights that you choose. So we're going to use a hypothetical example to model this. So suppose we have a collection of capital N labeled data points, okay? And we have labeled data, so this is supervised learning. And each data point contains 3 feature measures. So each of these x's is an element of R3, okay? And then each of the labels is an element of R2. It's a 2-dimensional vector. And these vectors look like this, 1, 0 or 0, 1 column vectors. So what do these indicate as labels? So for each of the N training points, we'll say that the vector 1, 0 indicates label class A, and the vector 0, 1 indicates class B. So for each of these data points, the labels are either one of these vectors where this vector indicates class A and this vector indicates class B. So this could say maybe lift left arm, lift right arm, or something like this. Okay, so this is what we're going to try to model with a neural network. So first, we need to design the network. So when we're building a network, we're going to have weights and biases associated with the interconnections between the layers and biases placed on the individual neurons. So weights and biases will be initialized to be random, and we will do this according to a normal distribution for now. Note that I'm going to give you things to read or literature to read where normal distribution, so initializing according to a normal distribution can lead in some cases to what's called a vanishing gradient or an exploding gradient, where when we try to calculate the gradient of our cost function, it disappears entirely or it blows up and gives nonsensical answers. For our purposes, in order to learn how to calculate the gradient and optimize on a neural network, we're going to choose a small neural network, one with 3 layers. So capital L is going to be the number of layers. So we're going to have 1 input layer, 1 hidden layer, and 1 output layer. Okay, so here is our network. We have 3 features for each of our data points. And then we have our biases here. We have 1 input layer where we feed our features in. We have 1 hidden layer. And then we have 1 output layer. And we'll discuss what these weights are, this notation here, in a moment. Oh, and we'll do it now. So the notation is a bit cumbersome, but bear with me. So W superscript L subscript IJ is the weight from neuron J in layer L-1 to neuron I in layer L. So let's pick one here. So this is neuron 1, neuron 2, neuron 1, 2, 3 bias. So this is layer 1, layer 2, layer 3. So for example, this weight here, we have, this is the weight layer 2, this is the weight layer 3. So weight layer 2, which is the superscript, 2 neuron 2 from node 1. So this is neuron 2, this is neuron 1. So it just says the weight from 1 to 2 in weight layer 2. So here, this is the weight in the second layer here from neuron 3 to neuron 2. So 1, 2, 3, 2, 2. So it's 2, 3. And this notation will make sense when we start looking at the matrix representation of these weights. Okay, so we've constructed a simple neural network, and all of these weights are initialized to be random numbers according to a normal distribution. Same with the biases, which, by the way, B superscript Li is the bias in layer L connected to node or to neuron I. So here this is the second layer, bias 1. So it's connected to the first neuron in layer 2. Okay. So next we have the feed forward phase. So this is the first of two major phases in considering a neural network. So here is our network. So for a given training feature xi, we input the features or the signals from this vector along with 1.0 into each bias neuron. So here we see that xi1 is fed into neuron 1 of layer 1, xi2 is fed into neuron 2 of layer 1, xi3 is fed into neuron 3 of layer 1, 1.0 is fed into the bias neuron for layer 1. And what we are going to do is say that A1, which we'll start to figure out what A's are soon, we're going to define A1 to be our input vector. So our input vector into our neural network is defined as A1, which is equal to the feature vector that we feed in. Okay. So once we feed these numerical values in, right, these are signals basically, each feature measure, so these are feature measures here, is then transformed by a linear transformation or a linear product with the layer 2 weights. So these are the layer 2 weights. So we're going to take a linear product of these values with these weights plus some bias and feed into layer 2, okay? So here we get Z21, Z22. These are what's called the pre-activation values at layer 2. So every layer besides the input layer is going to have a pre-activation value. And it's defined as the dot product of the input with the weights plus the bias. So if we look at this sum, so it's weight 1, 1, 2 times x1i, right? Plus weight 1, 2, 2 times x2i, or a21, plus this weight here times that value there, plus this. That's all this notation is saying. So it might be easier to actually think of this in terms of a matrix vector product, because now if we have Z1 and Z2, this is like a column vector right here. You see that, right? So we can think of Z2 as the weight matrix for the second layer times the input plus the bias. Right, so here's our weight matrix, and this is why the notation makes sense. So weight 1, 1, weight 1, 2, weight 1, 3. So it's A times there, but so A1 times there, A2 times there, A3 times that, plus B1 will give us our Z1 component in the second layer. And then for the second row here, we have A1 times this, A2 times this, A3 times this, plus B2. That'll give us our second entry in our column vector. So all this is saying is that we're taking a product of a weight matrix times the input signals plus some bias. So this is simply a linear combination, which is a vector, if you think of this as a vector, that makes up the input or pre-activation values, numerical values that are going to be stored in these neurons. So these are numerical values that are stored as the pre-activation of layer 2. Okay. Now this generalizes to if we had n, like lowercase n features, right? Then, and we had 2 neurons here, then we have a 2 by n matrix where there's n weights per each a neuron in the first hidden layer. Okay. So even though we're doing it on this simple example, this is always going to hold when you feed into your pre-activation values. Okay, so each pre-activation value is then squished by an activation function. In our simple case, we're going to use the sigmoid activation function that we learned about in logistic regression. And this sigmoid function will produce the post-activation values at layer 2. So all we're doing is we're taking these values and then passing them into Sigmoid to get a post-activation value, okay? All we're doing. And if we think of this in terms of linear algebra, we're just applying sigmoid to each entry in this two-dimensional vector. Okay, so these values are now stored in this hidden layer, right? And each of the neurons in your neural network, with the exception of the first one, which is just the input vector or signal vector, each of the neurons, we can store these numerical values, and these numerical values are telling us how much these signals are going to influence the rest of the network as we propagate through it. Okay. So once we have the post-activation values, this almost acts like a new signal, right? Like these are now signals that are passed into the next layer, right? And the strength of these signals is going to determine what the strength of the output of the next layer is. So we just repeat. So we repeat this step and now take a linear combination of this A vector, right, which with two components, with these weights plus some bias, to get the pre-activation of layer 3, right? So this, again, this is just numerical values that are stored in a vector, right? And then if we think about this in terms of linear algebra, Z3 is going to be this, right? So actually, I'm going to go ahead and just say, let me just fix this real fast. Where is the error? Oh, okay. So in general, um, we're going to have something like this. So even though we're just dealing with 3 layers here, this rule is always going to apply, where the pre-activation is simply the weights at that layer times the post-activation in the previous layer plus the bias at that layer. Okay, so in general, that's how we're going to compute the pre-activation. Okay, and here, if we look at it in terms of this matrix vector product, we just see that, again, this is why the notation works out so well. We have A1 times W11 plus A2 times W12 plus B13 will give us this pre-activation here, and then so forth and so on. Again, you have to be familiar with linear algebra operations, and just remember that this is a linear combination of these columns, and then we have this addition of bias vector here. So as before, we have a pre-activation, and then we just pass that into the sigmoid function to get the post-activation at layer 3. Okay, so because we've chosen capital L equal to 3, this is our final layer, which is our output layer. And we output 2 numbers, A13, A23. Okay. And sometimes this vector is denoted by O. So this is the output of our input, right? But so how does this relate to to making any predictions as to what the label is for x of I, right? Well, we compare this output with what the label was. So for a given input x of I, the neural network gives a prediction that this input is either class A or class B, based off of the maximum entry in our hypothesis vector, right? Our output vector. So for example, if our output was something like 0.78, 0.34, then the maximum of those would be in the 1 entry. So we could convert this to the column vector 1, 0, and that would predict class A, since class A vectors were 1, 0. On the other hand, if our output was something like 0.12, 0.44, then we would predict class B, because this vector, we would just say this is equivalent to something like 0, 1, which is the label for class B classes. And recall that each of these A's here is the result of applying the sigmoid function to a linear combination. And the sigmoid function is always a value between 0 and 1. So we're guaranteed that the outputs of our neural network are always going to have entries between the values of 0 and 1. Again, because we chose the sigmoid function as our activation function at each neuron. So for the given input x of I, our neural network simply defines a function that maps the input signals to some output in R2, some vector, some two-dimensional vector. But how is it doing this? Well, this neural network is a model that composes a sequence of functions that we wish to approximate our desired output. So this is where neural networks get their power from. Yes, we have linear combinations of functions, and then we have these sigmoid functions applied over and over again. But what this is really doing is it's taking a composite of a composite of a composite function, and when you take successive composite functions, you get much more richer functions as the output, right? And among all these possible outputs that we have under this composition, there are weights and biases that will exist that should give us the best approximate solution or best approximate hypothesis or output to what the label actually is. So once we have the design of the network here, we can start to tweak these weights and biases so that the output is closer to the correct output for this input. Since we know the label of this input, we can compare what we output to the label and then adjust the weights and biases accordingly until we start getting a better prediction. And that's where that's where the learning aspect of neural networks comes from. And we're going to do this using some optimization technique, such as gradient descent, batch gradient descent, stochastic gradient descent, or mini batch gradient descent. So as you can tell, if we think of this as a function of the W's and the biases, the input space here is huge, right? The variables for this function are huge. It's how many variables are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 variables already on this small neural network, right? And again, the output is a function of the W's, the weights and the biases, right? So if we're going to use something like gradient descent to optimize these W's and B's, we need to figure out how to calculate the gradient of this function. And that's where neural networks become messy when you try to dive into the details of calculating the gradient. This isn't as simple as something like logistic regression, linear regression, or something like this, because of the composition of functions. But provided everyone remembers the chain rule from calculus, then we should be okay, and we should be able to derive the gradient of this function, of this neural network, in a recursive manner. And that's what the second part of this lecture is about, and this is backpropagation. Okay, So in order to optimize the weights and the biases of this neural network, we need a cost function that penalizes the network whenever the weights and biases are bad. What we are going to choose is this sum of difference of squares. Okay, so notice here, the cost function is a function of our weights and our biases. These are our weights and our biases. So if our weights and biases are bad at predicting the given output for this x, right? Like if this output is bad and this output is bad. So suppose this was like 0.9 and this was like 0.2, and then this was 0 and this was 1, then if we sum the sum here, it's going to be high, right? But if A13 is close to the first entry in our label vector, if it's close, then this is small. And if this value here is close to this value here, this is the correct label again. If this is close and this is close, then this cost is going to be low, right? So this cost function benefits from having the correct weights and biases. It'll be lower whenever this is close to that and this is close to that. So we need to learn how to calculate the gradient of this cost function with respect to the W's and the B's, the weights and the biases. And then once we do that, we just apply gradient descent and we update the weights according to the gradient descent algorithm that we've discussed in previous lectures. But in order to do that, we need to know the partials with respect to W and the partials with respect to B for each one of these weights. Okay, so this is going to be a large vector. Okay, so the way that we're going to do this is we're going to focus on the output error. So for example, how much does weight 113, how much does this weight here contribute to the cost function error? Right? Is it a large value? Is it a small value? How can we determine this? Well, let's take the derivative of the cost function with respect to this variable. So the derivative of the cost with respect to the weight on the third layer, 1, 1, so from 1 to 1 neurons. Okay, so now this is our cost function, right? Now, which of these A's here is a function of weight 1, 1 on the third layer? Well, A1, right? A1, oh, this is a typo here. That should be A2. And let me just say, let me fix that in the previous slides real fast. That's because you want to compare this component-wise with the output. So the second component, first, and first. Okay. Okay. So here, the only output entry that is a function of A11, of W11 in the third layer is A1, right? So if we take the derivative of this with respect to W11, then this derivative for this piece is going to be 0. But here, we're going to take the derivative of the outside, so 2 times 1/2, times the derivative of the inside. So this is going to go to 0 because neither thing in here is a function of this variable, right? This variable here. This is the only one that's a function of that variable. So we take the derivative of the outside, and we just get A13 minus Y1I times the derivative of the inside. Well, this is just a constant here with respect to W11. So, but A13 is a function of this variable. So that's why I have the partial of A13 with respect to W11. Okay. So I'm gonna have to keep on fixing this. So now, what is A13? A13 is the sigmoid function applied to Z13, right? So all I did was just replace that by what it is, okay? So now, again, Z13 is a function of the weight 1, 1 on layer 3, right? So we take the derivative of the outside, which is just sigmoid prime of the inside, times the derivative of the inside. You see that? Derivative of the outside, which is sigmoid prime, times the derivative of the inside. This is just applying the chain rule over again. So here, what is Z13? So Z13 is just a linear combination of the output, the post-activation values in the previous layer times the weights, right? So A12, so A12 times this value plus A22 times this value plus the bias, and that gives you your Z13, right? So I just replaced that by the linear combination that represents it. So here, if we take the derivative of this expression with respect to this weight, we see that the coefficient of that weight is A12. And then this is 0 and this is 0. So this here is the partial derivative of C with respect to this weight. Now, this right here is what we're going to call our output error. So this derivative here, so what is this here? This is the derivative of C in the parentheses. This is the derivative of C with respect to A13, right? If we take the derivative of this with respect to A13, it's just 2 times a half times the inside times the derivative of the inside with respect to this variable, which is 1. So that is the derivative of this with respect to A13. And this is the derivative of the sigmoid of Z13. And we're going to call that the error, the output error. Okay, and this is the L is 3, was only 3 layers. So this is that value there. So we define the output error L at neuron J as the partial derivative of C with respect to the output J times the sigmoid, the derivative of the sigmoid times the pre-activation value. Now notice, this is kind of useful to note, that if we did this derivative with respect to B13, everything would be the same. This would be partial with respect to B up until here. And then if you took the derivative of this with respect to B13, it would just be 1, right? So there would be no A12 here if you did this with respect to B. So notice that the partial derivative of C with respect to B13 is just the output error, okay? Okay, so now I'm going to introduce some notation so that we can calculate the derivative of each of these weights, right? So notice that the only difference here, like if we wanted to look at the derivative of W123, nothing would change here except for this value right there, right? So let's consider the vector nablus of AC of partial derivatives of speed with respect to A, right? And then this thing here is called the Kronecker product. It's component-wise multiplication of vectors. So if you have 2 vectors with n entries, the Kronecker product of them is just the vector with n entries, where each entry is obtained by component-wise multiplication. See that here. So all together, so we need to fix this. Just fixing this again. So all together, what is this vector here? And again, whenever we can, we want to write these, we want to get rid of the subscripts and use nice, clean linear algebraic notation. So this value here, the error at the output layer, so here, this first vector, nabla AC, is this. The partial derivative with respect to A1, partial derivative with respect to A2, partial derivative with respect to AN. And each of those is equal to this difference. Okay? And this assumes that there's 1, 2, 3 n components in the output vector. Kronecker product this vector, so this is just sigmoid prime applied to each of those z's. It's equal to this, right? So this output error here, right? That output error appears in this product, in this vector. See it right there? This output error we're defining is, it's right there. And then the output error for this entry, right? It would just, each of these is going to be used in calculating the gradient. Because we see here the gradient here uses the first entry from here. The gradient of the next one would also use the first entry, so forth and so on. Okay, so now we've defined our output error. Now let's look at our neuron error. So the error at each of the hidden neurons, like how much, in other words, each of these weights here contributes to the values stored in the neurons. And we're going to determine how much those values affect the output of our cost, right? How much do they change the output? If we wiggle these weights a little bit, how much do those weights change the cost? Because those weights, when we wiggle them, change the values stored in the neurons, which in turn change the output of our neural network and, again, the cost of our loss function. Okay, so how can we do this? Well, let's focus on calculating first the partial derivative of this variable here. And we're going to need to do that for each of these, but let's see if we can do it and kind of generalize from this one to the other weights. Okay, so now if we take the derivative of this cost function with respect to W112, so which of these A's is a function of that weight? Like if you look at the composition over and over again, which of these is a function of it? Well, W112 affects A12, which in turn affects A13. So this value here is a function of that weight, but also W112 affects A23, which affects this value. So both of these outputs are functions of this input, of this weight. So when I take the partial derivative of these, I have to take the derivative of both of them, right? Because this is a function of W112 and this is a function of W112. And that's what this expression here is right here. So 2 times a half, this, right? So the derivative of the outside times the derivative of the inside, that's what this piece is right here. And then the derivative of the outside times the derivative of the inside, that's what this piece is here. Okay? So now, what is A13? Well, that's the sigmoid function applied to this pre-activation value. And then A23 is the sigmoid function applied to this pre-activation value. So that's all I did was replace that by what it is, just so I can see the function better. Okay. So now I just apply the chain rule again. So the derivative of the sigmoid is the derivative of the sigmoid times the derivative of the inside. Again, because this is a function of that variable. And then here, this is a function of that variable. So we have the derivative of the outside. This should really be a, where is it? Derivative of the outside times the derivative of the inside. Okay. So again, this is just applying the chain rule on this little piece right there. And then I'm going to have to change this again. change this. So now all I did was replace, everything matches up. So now what do we have here? Oh, notice A13 minus Y1I times sigmoid prime of Z13, that's the output error. So I replace this piece in the front by the output error at that neuron 1. And then here, the same thing happens here. This is the output error at neuron 2. So I replace that by the output error at neuron 2. And then what I'm left with is the partial derivative of Z13. So the partial derivative of Z13, partial derivative of Z23. Okay. Okay. I'm gonna need to fix this real fast. This should be a 2. And then we fix that on the previous slide too. No, it's already fixed. Okay. So then, okay, so this is the output error, which is here, right there, here, right there. And then the partial derivative of Z1, so that's this business right here. Partial derivative of Z23, so this business right here. So then if we take the partial derivative here, right, which of these pieces is a function of W112? Well, I see here that A12, this piece right there, that value, is a function of that value. So when I take the derivative, I take the derivative of the outside here, which is just W113, times the derivative of the inside. So that A12, that is this sigma Z12. So the derivative of the outside is the W right there, times the derivative of the inside, which is right here. And then here, it's the same thing. So this is Z23, which is also a function of A12. So then if I take the derivative here with respect to W112, I see that the coefficient will be W21. Okay? Because A12 right here, that A is a function of W11. So it's a derivative of the outside, which is just its coefficient right there, times the derivative of the inside, which is the derivative with respect to W112 of A12. Okay. I gotta fix this guy here. So I see this product here, which I can rewrite as, so I can factor out the derivative of sigmoid of Z12, and then I can rewrite this as this vector times this vector times the derivative of the outside, which is right there, times the derivative of the inside. And if you work out the calculus here, these are the same things, right? If I multiply these two things together, I get that times that plus that times this derivative, right? Because that's a common factor to both of them. But what is that derivative? It's precisely all of this right here. Okay. Let's make my adjustments again. So notice that when we take this partial right here, the coefficient of this is A11. See that? So what is this right here? Well, this is what we're going to define as the neuron error at a given neuron. But it's more than just this one piece. okay? It's this. So this is what we define as a neuron error at a given neuron in layer L. So for L equals to L minus 1 to 2. So notice here we have the weight matrix transpose in the previous layer times the errors in the previous layer, just like right here, weight transpose errors, Kronecker product, the sigmoid prime. Now ignore the A11, that's the full partial, but we still have this error here, which leads us to our partial derivatives. So here, notice if this is our error, right, then each of these components here, right, so this is like this value here times the A, right, times the A in the previous layer. And then if we took the partial in that previous slide with respect to the bias, we'd have a multiplication of 1 and not the A. So this is the definition of the partial of C with respect to the bias. So the reason why this is called backpropagation is because we use the error in the previous layer, in the L plus 1 layer, to compute the error in the L layer. So we calculate the error at the output. We use that to calculate the error at the previous input. Use that error to calculate the error at the previous input to that, so forth and so on. And whenever we calculate these errors, we immediately know the partials of the weights and the biases at that layer because we simply multiply the error times the appropriate A value, or just times 1 for the bias. So how does this work? Once we have the partials derived, well, we have the backpropagation algorithm now. So let's go ahead and do this. So for a given input xi, set the corresponding activation to be A1. So this is at the input layer. Feed forward, compute the pre-activations, and I should say and the post activations for each of the layers from 2 to L. Okay, so this is the feed forward part. This is really simple. It's just linear combinations and then applying the sigmoid function. So, but for each of these, we're going to save these. And then we calculate the output error, right? Which is this Kronecker product. So we take the partials with respect to C and partials of C with respect to the A's times the sigmoid prime of the Z's. Okay. And then once we have the output error, we're able to backpropagate this error recursively. So we start at L and we go to L minus 1, calculate this value, which gives us the error, the deltas, right? So we're calculating all the deltas. And then finally, once we've calculated all the way to the second layer, we're able to calculate the pieces of the gradient according to these formulas. And again, this should look familiar, right? The error times the value for the weights and the error times 1 for the bias. If we go back up here, the error times the value gives you the partial. Error times value is the partial. Right? And if I go up even further here, the error times the value is the partial again. So the error at that layer times the post-activation in the previous layer. That's what it's saying. And that gives you the partial derivative at that weight. And this is how you can calculate that. Okay, so that is going to be it for today's lecture. I encourage you, I highly encourage you to verify what's going on here. So for example, I calculated the partial derivative of this w. Do that for each of these w's, right? Calculate the partial for each of those w's, and then verify that the error times the input, I mean the post-activation, the previous layer, does indeed give you the gradient for this layer, the partials of the weights and the partials of the bias. If you don't do it yourself, you're not going to really understand it. And I tried with this example to work out most of the details for you, but realistically, if you really want to understand it, I worked it out for this weight, you work it out for this weight, this weight, this weight, and this bias, and then see how these equations actually make sense. In particular, this one. Calculate the error at this layer according to those weights, and then make sure that this partial is equal to the error times the input, just like it says right here. Okay? So hopefully this wasn't too messy for you. Next time we're going to write this using maybe vector notation, and then also program this using an example. Okay? Okay, so everyone stay safe. Thank you for listening, and I will post this lecture to YouTube after it finishes rendering.